Here's a question that sounds simple but shapes everything an agent does. Would you rather have a reward today or the very same reward a year from now? Obviously today. A reinforcement learning agent needs a way to express that same preference, to decide how much a future reward is worth compared to one right now. That single knob is the discount factor, usually written as the Greek letter gamma, a number between 0 and 1. It looks tiny and harmless, but it quietly controls how far ahead your agent even bothers to think. Let's dig in. First, let's see the problem the discount factor is actually solving. Count every future reward equally, and two problems appear at once. In a task that never ends, the total reward could balloon toward infinity, which is useless when you're trying to compare choices, because two different policies both just add up to infinity. And the agent feels no urgency at all. A reward now and a reward 1,000 steps away look identical. So it has no reason whatsoever to prefer sooner. The discount factor makes future rewards worth progressively less the further away they sit. A reward one step ahead keeps most of its value, while one far in the future is worth only a fraction. That single choice restores urgency and, as we'll see in a moment, keeps the math beautifully finite. So how does gamma actually reshape a whole stream of rewards? Watch the sequence unfold. Start with the raw stream of rewards the agent expects to receive from now on, one after another, stretching out into the future. This sequence is what we call the return, and right now, every entry in accounts fully. Now multiply each reward by gamma raised to how many steps away it is. A reward one step ahead is scaled by gamma, 2 steps ahead by gamma squared, and so on. Because gamma is below 1, distant rewards shrink surprisingly fast. Add all of those discounted rewards together, and you get the return the agent actually tries to maximize. Even in a task that runs forever, this sum settles to a finite, well-behaved number, which is exactly what makes the whole problem solvable. Mathematically, it's a geometric series, and gamma staying below 1 is what guarantees it converges. Finally, choose gamma to set the horizon. Roughly, 1 over 1 minus gamma is how many steps ahead the agent effectively plans. Near 0, it's myopic, chasing the next reward. Near 1, it's far-sighted, weighing the distant future almost fully. Strip it down, and the discount factor is quietly doing 3 jobs at once. It encodes a genuine preference for sooner rewards. $1 today really is worth more than $1 next year. And gamma bakes exactly that intuition into the agent's goal, so it doesn't dawdle when a reward is already available now. It keeps the math working. In a task with no natural end, the undiscounted sum of rewards could be infinite, but discounting turns it into a finite, convergent total the agent can compare and optimize. Without it, the objective itself falls apart. It acts as a horizon knob. Roughly 1 over 1 minus gamma tells you how many steps into the future the agent really cares about. Turn gamma up and it plans further ahead. Turn it down and it grows short-sighted. That one dial shapes everything it values. All right, let's lock in the essentials. The discount factor gamma, a number between 0 and 1, sets how much an agent values future rewards compared to immediate ones. Each reward is multiplied by gamma raised to its delay, so distant rewards shrink, and even an endless task ends up with a finite return. Near 0 makes the agent myopic, caring only about the next reward, while near 1 makes it far-sighted, weighing the long run almost fully. Set gamma too low and the agent ignores long-term payoffs. Too high and learning turns slow and unstable. So it's one of the most consequential dials in reinforcement learning. If tuning ideas like this fascinate you, we unpack plenty more over at Standarity.com. See you there.